Thank you very much. Thank you for this nice introduction. Yeah, I am looking forward to this topic. Recently, I have been doing quite a lot of presentations about AI-related topics, particularly about embeddings, vector databases, and so on, because many organizations, companies, schools, and many other organizations want to enable access to their company data, to their company databases through the power of AI. And this is exactly what we are going to talk about in the upcoming minutes. Let me quickly introduce myself so you know who you are listening to. As Tess said, my name is Rainer Stropek. I am a passionate software developer. I have been writing code for 30 years now, and I love writing code. I'm an entrepreneur. I have my own company, Software Architects. We are based here in Austria. And my second passion is working with kids and juniors. I am a mentor at a local Coder Dojo and a part-time teacher here at a vocational college. If you have any questions after my talk, feel free to link yourself up with me through LinkedIn or another social media platform, or just send me an email. I will do my very best to answer quickly. So without any further ado, let's dive right into the topic. I would like to structure my talk into multiple parts. The first one is for those of you who do not have a real understanding about what embedding vectors really are. It's a short one. I just want to bring everybody up to speed so we all know what we are talking about. For those of you who already know what embedding vectors are and who are only interested in the RAG pattern, just bear with me for a few moments, and then we are diving right into more advanced sessions. How do we apply embedding vectors? So let's start with the intro and let's bring everybody up to speed what embedding vectors really are. Let me give you an example. I didn't invent this example. It's a very famous example that describes, in my opinion, very nicely what embedding vectors are and what you can do with them. Imagine that you have to cluster people in a room based on their personality. What could you do? Well, what you could do is you could ask people a question and ask them to answer on a scale between 0 and 10. You could, for instance, ask, how open are you to new experiences? The result could now be used to draw a vector on, in this case, just a line. It's just a vector that shows how open I am between 0 and 100%. Now I can ask the next question about agreeableness, for instance. That will give me a second axis in my vector space, and with that I get a vector in a two-dimensional coordinate system. Because I have two answers and I can calculate them. I can calculate them to percentages and then draw a new vector. And I can go on and on and on and ask additional questions, and so on until I get a vector in an n-dimensional vector space, in an n-dimensional coordinate space. And that's essentially what an embedding vector is. You give the system some data. That might be text, it might be some sound, music, spoken words, it might be an image, and the AI system is capable of turning this data, in our case, in my sample, it will be text, can turn this text into an n-dimensional vector. What can we do once we have numbers, once we have a vector instead of just having some text or image information? We can use these embeddings for instance, finding similarities. So we can calculate the similarity between two people in our fictitious room to find out how similar they are when it comes to their personality. I can build clusters and so on and so on. So that is essentially what embedding vectors really are. Now, what can we do with these embedding vectors and how can we create them in reality? Let me show you that in a live example. Let me zoom in a little bit so you can see it pretty well. So in this small little example, I would like to draw your attention on this request here. Now, this is a request using the OpenAI API in Azure. So in preparation to this talk, what I did is I deployed some models, some OpenAI models to Azure. Why Azure? Because Azure is a very widely used system when it comes to corporates. So if you are working in a larger corporation, maybe an enterprise that works internationally or worldwide, you only have a few vendors with which you want to work with, and many companies nowadays use Azure. And in this case, I deployed OpenAI in Azure so that in an enterprise context, I could, for instance, integrate the deployment of ChatGPT into my virtual network. So nobody from the outside, from the public internet, can access my models. I can really embed them into my corporate network, into my virtual networks, and so on. So in this case, I am using a deployment which is called Embeddings. Now behind this Embeddings model, I'm using a specific AI model provided by OpenAI, which is optimized for generating embedding vectors based on text. And here you see the name of this model. This is the current model provided by OpenAI, which is recommended to calculate embedding vectors. And the input that I'm currently processing is, as you can see here, the quick brown fox jumps over the lazy dog. Now let's send this request. It's just a REST API. It's just a web request that we send out here. Let's send this API to the cloud, and what you see here is our vector. You see? This is the magic of the embedding vector. You might ask yourself, okay, how many dimensions are that? These are 1,536 dimensions, and that is the dimensionality of embedding vectors with OpenAI. Now the whole idea is that when I enter similar words or similar text passages, the vectors will also be pretty similar. So if I, for instance, enter king and I run the vector for king, obviously in real world you don't do that for words, you do that for paragraphs or text pages or whatever, you get a certain embedding. And now if I, for instance, enter queen, I can run this one, and here you will see a very important property. If you just compare the texts king and queen using their characters, for instance, these words are very, very different. However, in terms of meaning, they might be similar than when I compare king with, what could I do? Cat, for instance. Yeah? So, and that's the idea. The power of AI embedding models are that they compare or that they calculate the vectors not based on their similarity based on characters, but they generate the similarity based on the content, based on the meaning, if you want. I did that. I have that here in my presentation. What I did, I ran vectors for words king, queen, König, which is the German word for king, frog, and programming languages. And on the right-hand side, you see the similarity index. Now, what is the similarity? If you want to calculate the similarity of two vectors, you typically follow this mathematical formula. You calculate the cosine similarity. Now, luckily, we don't need this part of the equation. Why do we don't need this equation? Because OpenAI automatically returns vectors, embedding vectors that are normalized to a length of 1, to a magnitude of 1. So therefore, we don't need that part because that will always be 1. The only thing that we need in order to calculate the similarity of two n-dimensional vectors when it comes to OpenAI embeddings is the dot product of the vectors. So what I did for this table, I simply multiplied the vectors, the embedding vectors for king and queen, and this is the cosine similarity. The higher the value, the more similar the vectors are. And here you see important things. You see that king and queen, if you take a look at the characters, they are pretty different words, but when you ask OpenAI for the embedding vector, OpenAI says king and queen have the highest similarity when it comes to these two words, so the vectors are pretty similar compared to king and programming language, which is the least similar pair of these words. So that is the idea of embedding vectors. You take A word, a phrase, a sentence, some text passages from a website or a Markdown document or a PDF document. You calculate the embedding vectors, and then by calculating the dot product, you can say something about how similar these texts are. Not by comparing the characters, but by comparing the vectors. So that's the whole idea, and with this example that you saw here, you see that it is not complicated at all to do this embedding calculation. Calculating embeddings is a pretty cheap process. It doesn't cost a lot of money, so you can calculate lots and lots and lots of these embeddings. You can calculate thousands, tens of thousands, hundreds of thousands of embeddings in a pretty small amount of time, and you will only pay a rather small amount of money. That's a very important thing. Now, let's go back to the slide, sorry. Let's summarize what we can do with these embedding vectors. You take a large language model and you convert texts into vectors. Think about a company internal knowledge base that is not available over the public internet. You could take every article, split it up into chapters, for instance, and then calculate the embeddings for all these different chapters. What you will get back technically is an array of 1,536 dimensions, 1,500 float values. The similarity reflects the similarity of text, independent of the language. That means if you have two vectors which end at approximately the same area, they are rather similar. If you have two vectors which end at a rather different space in this vector space, they are pretty different. So what could you do? What could you do with this information? You could, for instance, look for duplicates. Maybe your knowledge base, you are not sure in your knowledge base whether you have multiple chapters or multiple text passages which are duplicates, which describe the same topic. You could use these embeddings to find duplicates. You could cluster the text areas. Think of a knowledge base. You could find similar articles. If you read this text, those other texts might already be of interest for you, and this suggestion can be calculated based on embedding vectors. What you could also do, and this is what the RAG pattern is all about, that I will talk about in a second, you could take a question of a user. I am looking for information about process XYZ in this customer project, blah. Then you can calculate the embedding of the question and compare the embedding of the question with the embeddings of all your knowledge base articles. And by that, you can find knowledge base articles which might be relevant for answering the question of the user. So we can do a so-called vector search. We are no longer using traditional full-text search algorithms where you are looking for the number of appearances of certain words, where you do word stamming and things like that. That is not what we do in vector search. In vector search, we calculate the embedding vector of the query, we calculate the embedding vectors of the work of the documents, and then we simply do dot products and compare the vectors. We will talk about vector databases in a second a little bit more. Obviously, you can combine vector search and vector algorithms with other search techniques. If the user says, I am looking for data about process XYZ, and the user knows that this is only relevant for, or that only documents are relevant, which come from a certain area chapter, for instance, of your knowledge base, you can filter the entirety of the knowledge base articles with traditional filtering and then apply vector search to a part of your knowledge base. And obviously, you will very likely get better results if you do that. So that's the whole idea of what embedding vectors are and how you can theoretically work with these embedding vectors. You will see examples about all these applications in a second. Now let's talk about what we can do with all that. Traditionally, when we think about AI, especially in this case OpenAI and ChatGPT, the end users use ChatGPT to access OpenAI. What we could do, if we want, we could write our own application and use the OpenAI API in order to access the AI provided by OpenAI. And of course, this one can run in OpenAI or it can run in Azure, as I showed you before. Now the question is, why would you do that? Just rebuilding the existing ChatGPT environment is not really interesting because you already have ChatGPT. However, you maybe want to limit the access to OpenAI to a certain network in your company, to a certain user group in your company, and then it might also make sense to simply rebuild ChatGPT and make it available locally, maybe restricted to certain users. Maybe you do some cost allocation where you know, okay, I want to know how much every single user spent using ChatGPT and things like that. You could do that. But what we really want, where things are getting pretty interesting, is if we want to teach our application-specific behaviors, we want to integrate application-specific logic and data, structured data and unstructured data. This is where it becomes really, really interesting. Now, let's take a look at how this could work. And this is where the RAG pattern comes in. The retrieval augmented generation pattern. It works, it's based a lot on embedding vectors, and this is what I'm going to show you step by step. Now the end user will send in the RAG pattern a question or a query or a command to our own application. This is an application that we write, we as a company, for instance. This application will not directly pass on the query to OpenAI because it's very likely that OpenAI cannot answer the question because the question might relate to a company internal data source. A company internal data source like, for instance, a knowledge base, the one that I mentioned before. So what we need to do is we need to take the question of the end user and send this question to some kind of database. That might be a relational database where you can use SQL, the structured query language. It might be a full text search, traditional full text search databases. But for our purposes here in this talk, we want to focus on vector search capabilities of databases. So you could use specific vector databases like Pinecone, Quadrant, or you can use existing databases that have vector search capabilities built in. For instance, Azure Search, the search service built in Azure, has a pretty strong vector search capability. Or maybe you are familiar with Azure Cosmos DB. It also has vector search capabilities built in. And what you see more and more is that all the traditional databases get vector search capabilities. Why is vector search so important? Can't we just take all the embedding vectors, calculate the dot product, and then compare everything? That would probably work if you just have some hundreds, some thousands of embedding vectors. But once you deal with millions and millions and millions of embedding vectors, the vector database has to be much smarter in quickly finding vectors which are rather similar and quickly excluding vectors which are definitely not similar. So we need indexing technologies based on n-dimensional vectors, and this is where vector search capability comes in. So the application takes essentially embedding of the question, sends the embedding of the question to the database and says, please calculate the similarity of all the embedding vectors in the database and give me back the, let's say, 5 most similar articles in our knowledge base based on vector similarity analysis. And then the database can take this data and return it to the application. It says, okay, user, you asked me that query, and I think those, let's say, 5 knowledge base chapters might contain the answer to your query. We could, in the application, now present the found documents directly to the end user. So the end user says, give me some data about process XYZ from our corporate knowledge base. We can simply say, hey user, these are 3 articles where you might find your answer. Then the user has to read these documents and has to find out the answer himself. But we don't want to do that. We want to go one step further. Once we have the question, and we have the relevant chapters from our knowledge base, we could again use OpenAI, for instance, ChatGPT in this case, to ask ChatGPT to derive the concrete answer to the question based on the knowledge base data that we just retrieved from the database. So what we essentially are going to do, we are going to write an intelligent prompt where we embed the result of the database query, where we embed the query, the question of the end user, and ask ChatGPT to formulate a nice answer that the user can then read and gets his answer pretty nicely. He doesn't have to read the documents from the knowledge base. He gets the answer right away. If he is interested in, he can always go back to the knowledge base articles and find out if OpenAI was correct or not. So what you see here is the general layout of the RAG pattern. And now I would like to go into a Python notebook and show you a little bit more how this works technical. Don't worry, if you are not a passionate coder like I am, you will understand, you will get the fundamentals, you will get how these building blocks work together. So we will not take a look at a lot of code, we will just focus on the most important things which are relevant to understand how this works in real life. Let me zoom in a little bit. Let me get rid of the menu items here and let's take a look at those examples. Now here I'm using Python, but obviously there are APIs for lots of different languages. You have OpenAI APIs for Go, for .NET and many other programming languages. And if your favorite programming language is not supported, you can always use the REST API, just sending HTTP requests as you have seen it before. Here I'm using the Python API in a very simple example. Now let's scroll down a little bit and let's take a look at the first part of code here. I will zoom in and we will take a look at this code. What you see here is I'm importing the API of OpenAI and I'm authenticating using an API key. Please note that this is relevant for OpenAI. If you run your ChatGPT, your embedding models of OpenAI in Azure, please do not use the API key authentication type. In cloud platforms like Azure, you have better capabilities. You can use so-called, let me write it down for you so you have a Google search term, managed identity. This is a very good authentication mechanism when it comes to running managed services in Azure, because with that, you do not need an API key anymore. It's secretless, it's passwordless what you do. The system uses Azure Active Directory for authentication, and the place where your code runs, maybe your Kubernetes cluster, that is the proof of identity. So no more secrets, no secrets need to be regularly changed, no secrets can be lost. So please note that this kind of authentication, I only use it for OpenAI and small demos. I do not use it for real-world applications. There, you should consider managed identity. That is just a side note, but we all know that security in cloud environments is really key, so therefore I want to be very clear about the messaging here. Now, here I'm defining a small helper function that we are going to use later on. And for those of you who are not that familiar with coding, let me quickly walk you through. This essentially uses the OpenAI client that you see on top here. It's calculating embedding vectors. This is exactly what I just talked about. It takes a string that we give here as an input parameter, and it uses the currently recommended model from OpenAI for calculating embeddings. So this small helper function is very, very simple. It simply simplifies, it reduces the amount of code that we have to write in order to come up with embeddings for a certain input string that you see here. Okay, nice. So now let's take a look at how this looks like if we calculate the embeddings for the sentence, "The quick brown fox jumps over the lazy dog," if we do that in Python. Let's do that. I will run this one and hopefully we will get an example. Now what you see here, this one, is the beginning of the embedding vector. As you can see here, I'm just limiting the output to 10 float values. So the entire vector would be 1,536 elements long, and I just print out, for example, the first 10 ones. And then I'm calculating the magnitude, the length of the vector, just to prove that this vector is really normalized. It really has a magnitude of 1. And here you see that this is the case. So OpenAI always generates vectors, embedding vectors, with a magnitude of 1. That helps a lot because then similarity analysis is simpler. So this is just the very basics. It's very similar to what I showed you here with this REST API, but this time you see it in an API, in this case, the Python API. Now let's try to implement the RAG pattern in a very simple way. I will scroll down a little bit, and what you see here is some description of fictitious cities. I came up with some fictitious cities like Emeraldine and Solara and Nebulea and so on. Essentially, I didn't come with it. I asked ChatGPT to describe some fictitious vacation locations, some fictitious cities where I can travel to see something. Some of these cities are in the mountains, are great for nature lovers, for hiking. Some of these cities are big cities where you can party and things like that. So these cities do not exist. And because these cities do not exist, OpenAI ChatGPT doesn't know about them. Of course it doesn't know about them. This is, let's say, a placeholder for your company internal data. This is data, this is a knowledge base that nobody else knows about. It's in your private possession, it's in your private network. This is not something which is publicly known. So this is the scenario here. So let's fill an array with all these cities. That should be pretty fast. Now we have a database with all these cities. So this database, this array, represents your company internal database, knowledge base, whatever you have. Now we need to calculate the embeddings. And what I do here is I simply loop through all the cities and calculate the embeddings, and again I store them in an array. And this is where vector databases typically come in. In real world, you would not calculate embeddings for 10 cities. You would probably calculate embeddings for thousands and thousands and thousands of text fragments. As I said, paragraphs of your knowledge base, documents of your knowledge base, maybe entries in enterprise databases, product descriptions, whatever you have. So in real life, you would have some kind of indexer that regularly goes to your database, gets out the text, split this text into decent size, and then calculate embeddings for every single text area. Then this embedding vectors, including some metadata like maybe the topic or a link to the original database, this is stored in a vector database, which is then optimized for searching. In my little sample, I want to demonstrate the general architecture. I'm not using a vector database because I only have 45 minutes. I would need at least double the time to also show you vector databases. So for now, please bear with me. We store our embeddings in a poor man's database in simply an array. We store it in memory. So let's calculate these things. Now this goes to OpenAI. So with a click of this button, we sent 10 requests to OpenAI, essentially exactly such requests, and asked OpenAI to calculate the embeddings for every one of these sentences or descriptions of the city. This is what we did. Now, next, we can start the query process. For instance, let's imagine the question, for vacation, I want to go hiking in the mountains. I want to really feel nature. This is what the end user said. We are working in a fictitious travel agency and the customer just asked us this problem. Now the question is, how can we find or sort the cities based on relevancy for this query? We want to find out those cities which work or which are perfect for traveling, for hiking, for nature, and so on. Now, As humans, we are pretty good in quickly reading 10 sentences and find out whether something is relevant or not. But you can apply this process equally with vector search to millions of databases. That's the whole idea. So in order to get started, we are going to also calculate the embedding vector of our question. So let's run this one, and that will give us the embedding vector of the question. So now we have 10 embedding vectors in our vector database, and we have one embedding vector for the question. Now comes the heart of the RAG pattern. The heart of the RAG pattern is essentially that we go through all the embeddings in our database, you see it here, and calculate the similarity, in our case the cosine similarity, which boils down to the dot product of the vectors for all our embeddings compared to the embedding of the query. And then we simply sort this one based on the similarity. So we get the highest similarity first. And you see, this process, this very, very naive iterating over all embeddings, calculating the dot product, sorting it manually in memory, this is something where in real life you would use the power of a vector database. Because this is only feasible for a handful, for some hundreds, maybe some thousands of vectors, but you are wasting a lot of precious time and memory and CPU time, and therefore costs. So if you have a larger database, this process that we see here works in the database. Okay, maybe at another conference I can do a talk about various vector databases. These things are awesome. They are fascinating pieces of technology. But in order to demonstrate the principle of the RAG pattern, I think we are good like that. So we simply iterate over it in memory and then sort the result and print the result, the sorted result at the end. So let's run this thing. Here, we didn't calculate any embeddings, we simply calculate the similarity. And what we see is the highest similarity with 0.8226 is the city of Aurora, a serene mountain city hidden in misty peaks where ancient monasteries and breathtaking hiking trails. That sounds pretty relevant for somebody who wants to feel nature and spend a vacation doing some hiking, for instance. The second one is also pretty interesting. An island city with rich maritime history surrounded by crystal clear waters, perfect for scuba diving and sailing. I could imagine that this is also interesting. A city built around an active volcano, also okay for hiking. Now let's take a look at the end. A futuristic city with floating building, neon lights, advanced technology. This is probably not the right thing when you are looking for nature, and that is exactly what we wanted. So the embeddings sorted the cities by relevancy, and it did a pretty good job. Let's visualize that in a chart. So what I did here is I'm using PyPlot, a library for visualizing things in charts. And let's run this thing. It simply takes the similarities and shows us the similarities here. And you see, by far, the most relevant entry here is Aurora. And then things are getting less similar to Nebulae, or whatever this fictitious city is pronounced like, is the least similar one. So in real world, we would obviously not tell the vector database to return us all the knowledge base article with all their similarities, but we will do something that we call a k-nearest neighbor. So we would say, give me the 5 most relevant articles. So the 5 vectors which are my nearest neighbors. So in our example, we could, for instance, take the 3 most relevant articles, which are the 3 most similar embeddings that we have in this database. So this is what we do here. Now let's try to provide this. We could immediately take the result, the first 3, give it to the user and say, this is what you might be interested in. But this is not enough. In our situation, we really want to use the power of ChatGPT in order to formulate a nice answer to our customer. So you see, we are going to do some kind of chaining of prompts. There are also libraries which are optimized for prompt chaining, like LangChain and so on. But here we are going to do it manually to demonstrate the principle. I designed a prompt for ChatGPT here. Let me read it for you. You are a helpful assistant in a travel agency. Customers are describing what they want to do in their vacation. Make suggestions based on the city description provided below. Now comes an important one. Only use the provided city descriptions. Do not use any other information sources. So we want to prevent that ChatGPT is using its very powerful and large repository of knowledge about the cities of the world, but we only want to present the cities that we have, for instance, in our product catalog. We also tell ChatGPT that if it cannot generate a meaningful answer based on the city and the given city description, it should say, sorry, I cannot help. If the user is asking for something which is absolutely not related to handling travel locations, we should simply say, sorry, I can only help with vacation locations. And then we inject the 3 most important, most relevant city descriptions that we retrieved from our vector database using embedding search into the prompt. So this is a placeholder where in this case I'm using the template functionality of Python in order to take the 3 nearest neighbors based on our vector search, based on our similarity analysis. To debug all this, we are going to print out the system prompt. So we are going to print the prompt including the things that we found. And then we are going to ChatGPT. Here we are using the ChatGPT Open API. Difficult word. The ChatGPT OpenAI API in order to answer the question. We are telling ChatGPT that this is our so-called system prompt. This is what we inject here. System prompt means that we tell ChatGPT how it should behave, how it should answer the question. And then we pass in the user query. So we are saying, hey, ChatGPT, this is how you should behave. This is your knowledge base. This is the user query. And now generate a response. I'm using the latest and greatest ChatGPT 4 Turbo model here, so hopefully we will get a good answer. At the end, in order to check our answer, I'm just printing the response of ChatGPT. Let's run this one. So you see, this is the prompt. You saw that one, and here we are injecting the knowledge base article, which we retrieved using our vector search capabilities. And then here we got the answer of ChatGPT. ChatGPT said, based on your interest in hiking and experiencing nature, I would suggest to visit Aurora, and so on and so on. That's exactly what we wanted to have. So this is what the user will see at the end. Everything in the middle is just something that happens internally in our system. So let's give it some additional tries. If I scroll up again and maybe I prepared some additional queries. For instance, imagine that we have a very different idea of vacation. We just want to say, in my vacation, I want to party, party, party. Let's see. Let's calculate the embeddings of our query. Let's do the vector search in our vector database. We obviously get a very different sorting here. We can do the printing of the plot again, and we see the top 3 cities are now very different. Now let's generate the new prompt. So let me click on that one here. So let's generate the new prompt. You see, we get different knowledge base. The part here on the top, this doesn't change. This is just a static prompt. And now the answer is very different. It sounds like Vespera would be an excellent choice for your vacation. With its reputation as a city that never sleeps and a bustling nightlife, you'll find plenty of opportunities to party. And if we take a look at the relevant knowledge base article, city never sleeps, bustling nightlife, cultural festivals, and so on, perfectly. Now what happens if we try to trick our system a little bit? Where is the question? Let me see. Here is the question. For instance, if we ask for traveling to an underwater city, of course, there are no underwater cities, so we can run our whole vector search. We will get some examples here. It would say, hey, go to this island city with rich maritime history, but this doesn't really answer our question. So let's see what ChatGPT is going to tell us. Sorry, I cannot help. This is exactly the response because we told ChatGPT that it should try to do its very best to derive the answers from the descriptions that we provided. But in this case, there is no underwater city, so it says exactly what I asked it to say. Sorry, I cannot help. And my last demo here, what if we ask something which is absolutely not related to any kind of travel analysis? We're just asking for the name of Bart Simpson's sister. Let's do the query. Let's go down. Let's run this prompt to ChatGPT, and it says, sorry, I can only help with vacation locations, because this is what we told the system that it should say when it comes to queries which are not related to vacations. Obviously, we got some responses from our database, but if we take a look at the similarities, we will see that we are in the low 0.70, something like this, and this is pretty different. So we could also add some additional functionality where we, for instance, do not generate any ChatGPT prompting if we don't find at least a similarity of a certain threshold value. I think you get the idea. So this is exactly how this vector search works. Let me go back to our slides and talk about one thing in particular. What about OpenAI GPTs and assistants? You might have heard that OpenAI presented a very new functionality a few weeks ago at their first developer conference. They were talking about custom GPTs and assistants. These custom GPTs are simply a pre-built version of the RAG pattern. What you can do with these custom GPTs and assistants, you can take your precious company data, for instance, PDFs, Word documents, Markdown documents, whatever, and ChatGPT, OpenAI, gives you a pre-built web portal where you can simply download these documents, and the whole process that you saw before with this RAG pattern and embeddings and so on and splitting of the text is done by OpenAI. It's essentially a pre-built low-code or no-code RAG pattern. However, for many larger corporations, they want to have a very specific behavior with very specific rules. So maybe this RAG pattern you are better off building this RAG pattern on your own, with your own business rules, with your own data, where you do not have to publish this data at all to OpenAI or somebody else. You simply keep the private data private and you only use the embedding vectors. That is exactly what I wanted to show you, and I think I am in time, and we even have a few minutes for some questions. So I ask, here is Tess. Hi Tess, I hope you liked my presentation. Yeah, I can answer the first one. That's pretty simple. The OpenAI models are so large, they are so elaborated, and they are so intellectual property of OpenAI that for OpenAI the answer is absolutely clear. Yes, you must send your text over the internet to either Microsoft Azure, so to your private deployment in your virtual private network, or to OpenAI. You must send it into the cloud. If you want to have a system which works on premises, OpenAI is, as of today, no option for you at all. Then you need to find some, let's say, open source models that can run locally, but then you are yourself responsible for running the models. And in my experience, those models are good, but they are not as good as OpenAI. So you have to decide, is data isolation more important than functionality? Then this is an option. Otherwise, you have to send your data. But you get a contract where OpenAI guarantees to you that this data is not stored and they never use this data to train their models. So on a contractual side, you are on the safe side. The data is always encrypted when it's sent to OpenAI. you cannot opt out from encryption at rest and from encryption in transit. So encryption is always there. I think what the question means here is whether it's possible to not share the data with OpenAI. And the answer is no. If you want to use OpenAI, you must use their services. You must send the data inside the prompt. If you don't want to do that, you cannot use OpenAI, ChatGPT, or embeddings, or the things that I showed you. Then you can use on-premises, for instance, open source models. The process that you learned in my talk is exactly the same. So you still work with embeddings, you still work with vector databases, you still work with some completion API, but you simply exchange OpenAI APIs through APIs which you run on premises. Absolutely, that's a very good question. For companies, enterprises who are concerned about data protection, I typically recommend using the deployment possibilities in Azure, because if you deploy ChatGPT and embeddings models in Azure, you can first choose the data center. So you can deploy the models in a European data center, maybe even within your home country, depends on which country you live in. You get enterprise-ready contracts. You have maybe an enterprise agreement, an existing one with Microsoft. That does not only relate to data security and privacy, but it also relates to payment issues. If you are a larger company, you typically have some payment contracts with large vendors, like for instance Microsoft, and therefore you do not need an additional vendor. So if you really are concerned about data sovereignty and the place where your data is processed and the location of the data center, just use Azure. That's the beauty of the cooperation of Microsoft with OpenAI, that you have the choice. That's a very important question for enterprise customers.